In the previous video, we studied estimation. In particular, the most important topic there is the properties of estimators, right? Unbiasedness, consistency, and what is the other one is efficiency, right? So usually, for these properties, you will actually need to get the distribution of your estimator and calculate its mean and variance, and then you can comment on the unbiasedness and consistency. Okay, those are quite important from a theoretical point of view. In 10.2, we switched to actually quite empirical side. Although, I already mentioned, we don't directly do a lot of programming or a lot of, data science, but nevertheless, we need to introduce some basic terminology that could help you better understand data. So again, here we only do the introduction level. We will not handle actual data. So to us, or to people in actuarial science, two types of data usually are duration data and loss data. So basically, the first one is about time. The second one is about size, right? Duration, like the duration of employment, the stay at a hospital, the survival time of a patient after a major surgery, etc. Right? You can also study the lifetime, of a certain group within a country. You can study the let's say the lifetime of an important part in an airplane, in a car, etc. Right? So those are about time. So those studies are about time duration. That's why we call the first type duration data. And obviously, to actuaries, they also care about, let's say, the loss data, right? So that would be the severity, the claim severity. Okay, so those two types of data are extremely important to us. Okay, we begin with an ideal case. Well, obviously, an ideal case is the complete case. You know everything, right? There's no missing data. There's no truncation, no censoring. So you have complete information about each and every individual. That is the so-called complete data. Okay, so here we let X denote the variable of interest. It can be time, it can be loss. X1 to Xn denote the values of X for n individuals. So those are random variables. Of course, once you observe, those become observations, then they are numbers. So we always use small x to denote the observations of a particular sample. Once you change sample, your observations are likely different. Okay, observations may be same, right? So let's say you observe the duration of a patient after a major surgery. Well, it's possible that different patients, survived for the same amount of time. Like, patient 1 and patient 2 both survived 3 weeks after the surgery. So it's possible that some of the x's are the same. Okay, so what we do next is, well, we select all the distinct values from x and call them y. So now all of them are different, they are distinctive. But of course, they come from x, so xy will be equal to at least one of the x, right? So those are from x's. Then because they repeat everything from the original data, so it's likely that for a particular yj, you may have more than one observations, so it's possible. So, but nevertheless, when you sum up over all m, j from 1 to m, you are supposed to go back to small n. Small n is the sample size, or the number of observations, right? So that's just an obvious result. A rather important and later on, maybe confusing term is the risk set, Rj, at time yj, right? So there will be n different risk sets. So the meaning of Rj is it measures the number of individuals in the sample exposed to the possibility of death at time yj. So later on when we have example, you will get a better idea. So basically, let's say you start with the first one, R1. If you have complete data, then R1 is obviously n. Means everybody is exposed to the possibility of dying at Y1, right? Because that's at the very beginning, that is the complete set, right? And later on, once you get the value to be higher and higher, you will kicked out several observations. Let's say if you observe the number of time survived after a major operation, there may be some patients, they were a little unfortunate, right? They didn't survive that long. So once you go to bigger and bigger numbers, since they already passed away, so they are out. So the number of patients will be smaller and smaller. But at the very beginning, it's simply all of them are exposed to the possibility of dying, let's say in the first week, right? All of them are exposed. Exposed does not mean they will die, right? It only means they are still in this time, right? So, but sometimes, maybe at this time, I don't know the value of R3, the value of Y3. Let's hypothetically assume. So it's 5. So meaning right now I want to know what would be the exposure set or the risk set at 5. Then I have to exclude everybody who didn't survive to 5, right? Because it is the exposure set. Those who already passed away before week 5 have to be excluded because we already know they didn't survive, right? And when we talk about the risk set, would be the patients, all the patients who survive to week 5, then they are exposed. It's possible that they will die, right, in the next week. Okay, so that's the exposure set, right? So in some sense, exposure set is the survival set, right? So it includes all the survival members, right? So that's why it gets smaller and smaller. At the beginning, you have to include everybody because that's the very beginning. R1. Nobody dies before Y1. Y1 is the smallest number of survival time. Okay. So with that in mind, let's do an example. Okay, then everything hopefully will become more clear to you. Let's say we have a data set. It's very simple. We only have 16 observations, right? So it's about failure time of a machine part. So the first one failed at 2. Well, I don't know the time unit. What's the time unit? Well, you can randomly put some time unit. Let's say 2 hours. Right? So the first unit died within 2 hours, etc. The last one, the longest one survived 24 hours, okay, or 24 days, 24 months, whatever you want. So first we need to count all the distinct numbers, right? So for instance, here we need to put them together. Here we need to put them together. Here we have 3 8s and 2 18s and 2 24s. Okay, so we can easily collect the same ones. So we can label them from, well, instead of 16, we only have 9 different observations, right? The value goes from 2 to 24. So, well, we know no parts failed before 2, right? So 2 is the first failure time, okay? So now we want to somehow study the risk set. So this is simply the count number. So 1 means there's only one observation with value 2. Right? 3 means there are 3 observations with value 5. Right? That's from the original data. So this are very easy to figure out. Right? And we list them from the smallest to the biggest. Okay. And well, you can check when you sum up, you should get 16. Now let's take a look at the risk set. At the very beginning, everybody is included. Oh, here's all the parts are included. So you have 16 parts. Okay. Then moving to the second one, the exposure set, it becomes 15. That's because 1 is already gone. So will be 16 minus this. Then it will give you 15, right? The previous total, well, 16 are survival, right? So the survival set has 16 parts. 1 failed at 2, so you have to take it out, right? So you take out this one, then the current number of survivals is actually 15, right? Then you minus another one, another part failed at 3 now. This is 3. Then you get 14, right? Then you have 3 parts that failed at 5. So take them out, you get 11, etc. Right? So it's very easy. Right? So the previous one minus the number of parts that failed at the given time. Then you will get to the next level. So for complete data, it's very easy to study, to somehow come up with this table. For incomplete, it's a little more complex. Okay. This is a different example. We have 20 claims. Okay, and they are arranged already from the smallest to the largest. So no deductible, no policy limit, meaning no truncation, no canceling. We want to do the same thing, right? So meaning we want to get all the distinct numbers. We want to count WJ, and then we study the risk set RJ. So it's very easy actually, right? So we count from the smallest to the biggest, right? So those are the all the distinct values. This is the count column. You count the number of observations for each value. Obviously, in total, you should have 20. That explains why the first risk set is 20, right? 20 minus 1 gives you 19. Right? 19 minus 3 gives you 16, etc. Right? It goes on. So it's very easy. So what's complex? What's complicated is the case of incomplete data. Okay, this is likely the real case we face. In certain studies, the researcher may not have complete information. Actually, that's in pretty much all studies, right? About each individual observed in the sample. There could be different scenarios. Okay, so let's say here we consider survival time of patients after a surgical operation. So whenever you have a study, right, you have a beginning time, you have an ending time, right? You do not go back to the very beginning of the surgery, or well, there's no way to continue forever, right? So you must start somewhere and end somewhere. Okay, so you begin here and you end here. But it is possible that someone received the operation before the starting time of this study, right? And it is also possible that someone by the end of your study is still alive, right? Then we don't exactly know the survival time for those people, right? So we only know it should be greater than or equal to something. Let's say this person operated at this time, but is a lucky person. By the end of the study, he's still alive. So we know his survival time is greater than or equal to this period. But we don't have exact equality because this patient is alive by the end of study, right? But of course, it is possible that someone who received the operation here and died at this point. So then we know exactly the amount of survival time for this particular patient, right? So we have the left truncation and the right censoring, right? Censoring means, you have greater than or equal to. Truncation means someone received the surgery before the start of your study, okay? Oh, of course, those are the two standard scenarios. It's also possible that you might have a missing data, right? So you observe this patient, but somehow later on, you lose track of this patient. You have no further information. He or she is not cooperative, right? Moved to a different state, and you couldn't track. That's also possible, right? That's missing data. We don't discuss missing data here, but of course that's well possible. There are different techniques of handling missing data. Right? Obviously, the easiest one is simply to discard missing data, right? Okay, that's the part I already mentioned. It's possible that we have left truncated. That means this individual is observed from a population that not available, who do not survive till the beginning of the study. That's left truncated. Those are the in my previous graph, that would be this. Someone received the operation and then died before the beginning, then you don't even observe this person, right? Right censored means the data is greater than or equal to, right? This patient actually survived more than the length of the, not the length, but survived by the end of the study, right? So there's no way to get exact number because the study has already come to an end, right? So you only have partial information. Okay, the left truncated part, that's simply we cannot do anything because you don't have that information is not available. Okay, so that's the left truncated. So we need some definitions to help us to move further. Some kind of notation. Okay, that's because we have some patients who received operations before the start of the study. We use D to denote. So if D equals 0, that means there's no truncation. Meaning for this for patient I, the operation was after the starting time. Okay, so the operation was done after the beginning. Okay, but we could put di greater than 0 if it's left truncation. So the operation was done before the study begins. Well, the greater than 0 sometimes might cause confusion because we may tend to think this is negative number, right? It's just that we don't like to report. So let's say here, so let's say here is time 0. At time 0, study begins. Okay, but someone might have his surgery done before 0, right? Then that refers to d greater than 0. Okay, let's say 2 weeks before. So technically speaking, it should be -2, right? But we label it as 2 instead of -2. This is just a convention. Although, like in the mathematical term, a -2 might make better sense because it is ahead of on the left-hand side of 0, right? So you should put negative. But nevertheless, we tend to use a positive number to mark. So instead of marking it as -2, we mark it as 2. Okay, for any surgery after time 0, it will be labeled as di equals 0. That means you have full information. Well, it's observed after after 0. Of course, you will have the information for that. And then we use X to denote the survival time. So let's say for another patient, the operation was at week 1. He passed away at week 5. Then for this particular patient, let's call it XJ, would be 4, meaning he or she survived the 4 weeks after the surgery. Okay, but as already mentioned, right, it's possible that someone survived longer than the end of your study, right? So in that case, we will have to use a different number. So let's say we have another person who received the operation at week 5, the end, let's say 12 week. Week 12 is the end of my study. Well, I don't know for this particular person. Let's call XI or XK, right? So XK is actually unknown. We don't know the exact amount of weeks this patient survived, but we know this must be greater than 12 minus 5, minus 7, so it's 5. So in that case, we do not use X. We only use X to denote equality. In this case, we put U. We know the survival time will be greater than or equal to 5, but we don't know equality, unfortunately, because the study already ended by week 12. Okay, so as you can see, either you have equality, then it's X, or you have inequality, then we use U to denote. So we have two things, right? For D, either it's 0 or greater than 0. Then for the survival, is either X or U. X means equal, U means greater than or equal. Okay,